Okay, I think we'll get started. So today is the first lecture in this mini course on the Gibbs Phase Rule. The Gibbs Phase Rule really boils down to a mathematical counting problem. So it's elegant in that way. We can really break it down into really self-evident, just counting up some things and then applying some constraints. And so that's what we're going to do today. We're going to limit ourselves to non-reactive systems. So this could be a mixture of glucose and water. It could be just water itself, water, ice, and vapor. No chemical reaction taking place. Later, the next lecture, we'll talk about incorporating a chemical reaction, and we have to be there's a little bit of subtlety there, but it's still relatively straightforward. But today we're going to focus just on the non-reactive systems. And we need a little bit of definitions here. We need the idea of a phase. So a phase is a single homogeneous part of the system. So, for example, in the case of, let's say there's two phases here, alpha phase, beta phase. If this was water and this was liquid water and ice, for example, we would say that there's two phases there, the liquid part of the liquid part of the water, and then the solid part of the water or the ice. Now, in the system of like water and glucose, that's mixed, and that's completely homogeneous at the chemical. It's mixed at the single chemical level, so at the molecular scale. So it is homogeneous, and so that would be a single phase. Now, if you might imagine, say, if you take oil and water and mix it up, and it makes this emulsion, that is not mixed at the molecular level scale. It's heterogeneous at the molecular level of scale. So even if they're really fine bits of oil and water mixed together, it's still oil and water, and so that would be two phases. Now, the number of components in the system is going to be a little subtle. Today, it's very simply just what species are present. So water and glucose, that would be two components. Water, that would be one component. When we have reactions, a little more subtle there, but we'll take care of that next lecture. Okay, so how we're going to go about today is we're going to derive the Gibbs Phase Rule, and we're going to do so by getting the individual pieces of this mathematical counting problem. And the first thing we're going to do is review some ideas regarding equilibrium. So we're not going to show in a real rigorous way. We're just going to take this information here and then go forward from there. All right, so let's imagine a single compound, A. So you can just imagine water, and then the Greek letters here are the different phases. So let's say ice, solid water, and liquid water here, and we can write as a reaction an individual water going back and forth between this phase, right? So we have this dynamic equilibrium that occurs between the ice and the water. Now, if we're at equilibrium, well, even without it being at equilibrium, we can, for any homogeneous system, we can specify all thermodynamic variables. Any closed homogeneous system where the number of particles in a given part of that system is not going to change, we can categorize that with two variables. Now you can choose any two thermodynamic variables. Very convenient choice is often temperature and pressure. And when we choose temperature and pressure as our independent thermodynamic variables, then the Gibbs free energy is the natural dependent thermodynamic variable that will be the most natural to talk about in terms of an equilibrium. Now, in this case, the number of particles in one phase to another phase can change. So there's another two variables that have to go into the dependence of this Gibbs free energy. And that would be the number of moles of A in the alpha phase and the number of moles of A in the beta phase. Now, if we write the expression, the physical expression for delta G, the first part, and I know I'm just jumping this in here, so if you've had some thermodynamics, this will be familiar to you. If not, just sort of take it and kind of pop out the other side, and we'll go on with the rest of things. But this is our bit of dg if we have a closed homogeneous system. Well, now we have this ability to go back and forth, so we need to have these terms associated with the different number of particles in each of these phases. Now, they're driven in or out of the phase by the chemical potential. And so this mu is chemical potential. Again, we're not going to be talking about what chemical potential is in this mini-series, so I'm kind of assuming you have heard about that. If not, it's not necessary to understand what we're going to be talking about in this course, mini course. But if you do, great, that will kind of connect there for you. Now, one thing that's nice about Gibbs free energy and the choice of using temperature and pressure as natural variables is they're often, or as the independent variables, thermodynamic variables, is that they're very often easy to control. So we can, and measure. So we can easily measure temperature, we can easily measure pressure. We can also control that pretty well. So we can use a temperature bath to maintain some kind of system at a constant temperature, also pretty easy to maintain a constant pressure. So what that can do then is allow us to get right down to the chemistry that's going on, or the physical chemistry that's going on amongst the particles. And so if we go with a constant temperature and pressure, we see these terms drop out. And that leaves just the material terms. Now, at equilibrium, the condition for equilibrium is that dg is 0. So that's a criteria for equilibrium. And again, that's very familiar to you if you've had some thermodynamics, even some general chemistry thermodynamics, and certainly if you've had any physical chemistry thermodynamics. So if this is 0, then we have this equaling 0. Now we're going to make a definition here. We're going to say that dN is equal to dNA in the beta phase. Now, if that's how we define dN, then it's equal to negative dN in the alpha phase. So let's just think about this for a bit. For every molecule that goes from here to here, this increases by 1 and this decreases by 1. So for a dN to go up in here, then this will decrease. This will be a plus dN minus dN. Okay, so the dN alpha and the dNA alpha and the dNA beta are equal but opposite. Okay, so we then can plug the dN in here for these individual values, and so we have this. So notice what's happened here. In general, we've had 2 additional variables. So the Gibbs free energy is a function of temperature, pressure, and these 2. That's 4. But the condition of equilibrium has linked these 2. We can't change one without the other. And that's a critical sort of underlying idea in the Gibbs phase rule. Okay, so we've written this out. We now have a common dN that we can pull out, and we look at the result of an equilibrium gives us this so-called equilibrium equation. This is another criteria for equilibrium is, oh, this is incorrect here. And so what we see is that the equilibrium enforces or gives rise to an equation that links the 2 phases here. Okay? So in a sense, we have linked these 2 guys here due to the equilibrium. Okay. Now, again, as I mentioned at the beginning, let's not let any chemical reactions happen. We have only one species, A, so one component, and let's now just extend this a bit. Let's say we have this original equilibrium, but then a whole bunch of other phases, say P. number of other phases, as many as we want here. And there's an equilibrium now among all these phases. So for example, water has solid, liquid, and gas. That would be a 3-phase system there. Okay, well, what would we get? For each one of these, we're going to get a equilibrium equation. And so the alpha beta here, then this one would be beta gamma, and so on and so on and so on. And so if we have 3, we're going to get 2 equations. If we have P, we're going to get P minus 1 equilibrium equation. So this is one part of this mathematical counting problem that we're going to set up. So we have now counted all the number of equilibrium equations for any number of phases, right? So this is now general for any number of phases, but it is specific for only the case of a single component. Well, let's add some components, A, B, C, D, all the way out. As many components as we want. Now again, for this case, you can just think of components as a different chemical species. And we'll see that that isn't exactly what they are in the next lecture. So we now have ABC in some kind of phase alpha, beta, and so on all the way down. Now we're going to get for the A, we're going to get P minus 1 equilibrium equations. For the B, we're going to get P minus 1 all the way down. And so we're going to get, now I got to be careful here now. This is a different C. So there's going to be a clash of notation here. C is the number of components. So this is number of components. This C is just A, B, C, labeling the species. Okay, so we have now counted. We have another part of our counting problem. This would be the case now for C components. We see this term coming in here, and it's just multiplied by C, the number of components. Okay, well now let's look at another part of this counting problem. If we've got, say, let's just imagine a binary system of species A and species B. If we think of things in terms of mole fraction, so that's a mole fraction is a form of concentration. It's more convenient than molarity or molality when thinking about and deriving the Gibbs relation. And that is, you could think of mole fraction as sort of a percent. It is a percent. So if you were to grab one molecule out of the system, what is your chance that that would be species A versus species B? Okay, so the total sum of all the different mole fractions has to equal 1. So it's simply basically a probability problem, and you're asking, okay, what's my chance of getting any molecule? Well, that's going to be 1. And so this provides a relation now between the number of components, right, and how many independent concentrations we have. So we have just 2 components. The mole fraction A plus mole fraction B equals 1 forces now one independent. So for example, XA plus XB equals 1 means we cannot change the amount of X without changing the amount of B, or the percent of X without changing the percent of B. So we can write B as a function of A. So there's not 2 independent variables, but there is just 1 independent variable here. And so let's think about that for, well, let's do it for three components, right? Then the mole fraction of C can be written as a function of A, but also B. In order to specify C, you would need to know both A and B based on this equation. So for an arbitrary amount, we get C minus 1 independent variables. So for the case of 2, we had 1 independent variable. For the case of 3, which we just did there, we had 2 independent variables. For the case of C, we have C minus 1. Right? That's another part of this counting problem. And that would be true in each phase. So in each phase, you specify the mole fraction of each in each phase. So that's going to be P times that independent variables. Okay? So, and these are concentration variables. So now we want to cast this as what are the degrees of freedom of this system. And that's the heart of the Gibbs Phase Rule. The Gibbs Phase Rule tells us how many degrees of freedom our system has, or that is how many independent variables. So let's look at this count now. So we found the independent concentrations, and there's our count from that. We have automatically 2 more because of our temperature and pressure, right? So these are the concentration independent variables, and then these are the temperature and pressure. Then we have a certain number of constraints that these must fulfill. These constraints reduce, each constraint reduces by 1 the degree of freedoms. So we have minus this, right? So these are the constraint equations. These are independent variables, but they're not completely independent when they're at equilibrium, because we have these equilibrium constraint equations. So we can multiply this out, PC minus P plus 2 plus CP plus C, and then we can cross out the C times P, and we get, finally, the Gibbs Phase Rule. So this is the Gibbs Phase Rule. We've derived it now very carefully based on essentially self-evident counting. Now this isn't a completely rigorous proof, but it's a nice physical argument and simply a counting argument. Very easy to see where all of the components of that mathematical counting problem come from. Now, let me say just one thing. We sometimes will see the Gibbs Phase Rule like this. We will most often work with this. This is called the condensed version, and this is when you'd be talking about just things involving liquids and solids, so like the ice and liquid water example, but not water vapor. And that's because the pressure really doesn't have a lot of effect. It's a very negligible effect compared to temperature, very, very negligible effect compared to temperature on condensed systems. So in a sense, the pressure is sort of frozen out of the equation. And so we're left with really only the temperature as the independent variable. So you're always good when this goes. Sometimes you might see this, or it might make even better sense to use this. But we just got to know that what that's doing is saying, okay, the pressure is not affecting the system in a way that makes it variable. All right, well, let's just conclude with a few examples then to kind of solidify this. So see if you can kind of work through these with me. So let's just do that ice water example. So let's say we've got this beaker of water, and it's got some ice in it. Okay? And it's at equilibrium. So we're at say 0 degrees, the system's at 0 degrees Celsius. Okay, so let's now count the number of components. It's just 1 because it's water. The number of phases here is 2. So the number of degrees of freedom then would be 1 plus 2 minus 2 equals 1. So there's 1 degree of freedom given by the Gibbs Phase Rule. Now we'll go into this in more detail. Here we're just showing, we're just going through kind of how to calculate the degrees of freedom based on what we see here. We'll understand the more what this kind of means physically later. Okay, so there is one case. You might be familiar with the fact that water has a triple point. So at the triple point, it's a very special case where we have solid, liquid, and vapor all in equilibrium. And so let's look at the number of components here, still 1, because we're looking at just water. Number of phases, 3. So the Gibbs phase rule then would be 1 plus 2 minus 3 equals 0. 0 degrees of freedom. And if you know something about the triple point, you know that that is a very special temperature and pressure in which this occurs, the so-called triple point of water. And so any deviation from that, we're off of that triple point. So it is really a fixed, there is no degrees of freedom. So that's what that means. Let's let's look at the power of the simplicity and generalness of this Gibbs phase rule. So it is not always useful to really get going. We have to get into some real more detailed thermodynamics. But the fact that it's so simple can say some important facts about nature and prove those facts very sort of easily and straightforwardly. So it's harder to think about just this particular case, but let's propose we have for a single homogeneous system. Can there ever be a single homogeneous system that has 4 phases in equilibrium? Right, so that's our question. Can we ever have that for a single homogeneous species, chemical species? Well, let's address that question here. So if we have a single species, we have just one. We've now said that we have 4 phases. And so if we go 1 plus 2 minus 4, we get minus 1 degrees of freedom, which says that it's impossible. Okay? So it makes a strong statement in the fact that it's completely general. There is no way for us, any kind of single chemical species, to have 4 phases in equilibrium. So what are these 4 phases? With water, in the water case, we know that there's different types of ice. Those are different phases. There's no quadruple point for water, say where solid ice of one phase, solid ice of another phase, and then liquid and vapor all come together. So it can't happen because of the phase rule. The phase rule says it can't happen. Okay, let's just do a couple of, maybe just one more example here. Let's use this water and glucose example we had mentioned. Okay. So now the number of components is 2. The number of phases is equal to 1. So the number of degrees of freedom here is 2 plus 2 minus 1. And so we get 3 degrees of freedom. Okay, what are those degrees of freedom? Temperature, pressure, and then the mole fraction of water and glucose. Not water and glucose, sorry. Mole fraction of, you could choose either one of those. The mole fraction of water fixes the mole fraction of glucose, so they're not 2 independent variables. So let's say temperature, pressure, mole fraction of glucose would be the 3. All right, so this is the derivation of the Gibbs phase rule. We've worked through a few examples here. We've even used it to prove that no single substance can ever have 4 phases in equilibrium. We did see that it is possible for a single substance to have 3 phases in equilibrium, and that is that one example of that is the famous triple point of water. Okay, so that's it for today. Next lecture, lecture number 2, we're going to add chemical reactions, and then that gets us completely general then. And then after that, we will go on and talk about some situations where it's nice to look at the Gibbs phase rule, kind of complements some of the thermodynamics that one would talk about in those areas. So we'll talk about mixtures of solutions that form what are called eutectics, and then we'll even look at, so we'll look at binary systems, and then we'll look at trinary systems, so 3 components. Some interesting things there that we can say using the Gibbs phase rule.